of C++, right? Okay. So today's topic is kernel bypassing. But what I'd first like to do is
And
let
today,
us,
just a
yeah.
second, today is the mock session. This is just for kernel bypass, which is of HFT syllabus. And this is not the starting of the syllabus. This is just for the mock session. You guys see this thing and then decide to, like you are interested to enroll this course or not. So yeah, Abhinandan, you can continue.
Okay.
Yeah.
So, when we talk about kernel bypassing is all about, reducing latency, right? Because in trading applications, every microsecond counts, and, the general tech stack that is used in normal applications or the Linux kernel, it is built to run multiple applications, a lot of applications, which is the user does not care if the latency goes in hundreds of microseconds or 200 microseconds. But for understanding kernel bypassing, what we first need to understand is how the hardware is structured. है ना? So when we talk about normal network calls, for example, your application is running on like you have a 4-core CPU, and if you go to the Linux processes tab, you'll see that there are like 1,000 threads running. So what the kernel basically does, it manages all of those threads and assigns CPU time to all of those. So our particular objective when we're working in trading is to, shed dead weight off, shed any kind of processing that is not required for us. We have to shed that off. And the first part of it is running an application on a single core that is not interrupted by the Linux kernel. That is the first part. And when we're talking about hardware, kernel is also a thread. Kernel is also process. And as soon as context switching comes, when we're talking about kernel and any kind of processing, when context switching happens, your CPU has to move your function call stack and the memory stack to the cache or to the memory, and the load the stack of the other thread. So what we want to do is we want to set up a system that is streamlined, that is long running. So when we talk about kernel bypassing, the first thing when you like, just give me 1 minute. I'll just go to the next slide. Okay. So the standard path, what happens when you make a network call is for example, let us talk about your network card receives a packet. The network card sends the packet to the kernel process. Now the kernel process sets up an interrupt, and the kernel process is basically a long running loop. So it has a lot of objectives, a lot of tasks, but it has to manage all the threads, has to manage which CPU is allocated to which thread, and it has to schedule things. Now, whenever we talk about scheduling, that directly implicates latency because something is not happening right away. What we want is a streamlined process where everything happens immediately. So what the kernel does is kernel schedules the packet to be received to your application, and then your application receives that packet through polling and any kind of ways. So what happens is when you have this kernel in between your network card and your application, there is a form of IPC, which is inter-process communication. Now, inter-process communication in itself, when you're developing C++ applications, is when you have two threads communicating with each other. Any kind of IPC, any kind of IPC introduces latency. And what we want to do is avoid all of that latency and avoid any kind of context switching overhead. So we want packet predictability. We want कि जिस point पे we in our network card at any point, when the packet is received, our application can directly communicate with the network card, and it does not have to go through all of this operating system management. So another important thing to note is like when you have an application running in C++ and you want it to have the best performance, you will use CPU pinning, and you will use CPU pinning and core isolation. So basically, if my application uses 2 cores, I will isolate those 2 cores from anything else. So nothing is scheduled on them. My applications that is using the 2 cores and it has 2 threads, they are long running. They are not being interrupted. The second part is I want my application to communicate directly with the network card. Now the network card is like a mini CPU in itself. It has its own processor. It has its own memory. What we are trying to do when we talk about kernel bypassing is connect and contact with the network card directly, or basically access the memory of the network card directly. See, like our goals currently is talk directly to the hardware and cut the kernel out of the critical path. I think this is the same thing, kernel bypass concept. Now, the like I've already explained to you on Linux normally handles packet handling. So what happens is your network card receives the packet and the interface card gets a packet from the wire. When the network card receives a packet from the wire, it triggers an interrupt and tells the CPU like, hey, data has just arrived. And what the kernel does is kernel does not process the packet directly away. It schedules it and does a lot of the other process it has in its loop. And after that, it fires that packet to your process. And then what it does is interrupts your process, your application long running process. And what happens is your thread pauses for a bit. Your application pauses for some time. And what we want to do is we want to avoid any kind of pausing. We want to directly access the memory of the network card, and we want the network card to directly access our CPU memory. Now, these are some of the benchmarks that I've gotten. For example, kernel, there's a lot of methods you can use to optimize a kernel also. For example, the kernel has a dynamic, kernel has a queue for each of the CPU that you have. For example, if I have a 12 core CPU, each of my CPU will have a queue, receive and transfer queue, RX queue and TX queue, associated with those cores. And what the kernel does is it shuffles them around for specifically for balancing. And that is all of these things are not ideal for a system that is built to do one single thing very good. It's built for a system that is supposed to do a lot of things in a balanced way. So as you can see, the throughput difference between an unoptimized kernel and when we use DPDK, which is basically direct access from the network card to our application and back, we have a lot of difference in performance. And what I have on the other side, where we're talking about ExaLib, ExaLib is currently Cisco's library, Exanic network cards library. Cisco has acquired Exanic. So it is currently the lowest latency solutions available. So when you can see the performance metrics here, when you were sending raw frames, we're in the sector of 700, 800, lower than a microsecond latency. So what we want to do is, uh, first we have to build a system that is, our application has to be extremely low latency. So if your application is not configured properly, or if your application is facing context switching and your system is not optimized for running the application, using DPDK or Exalib or any kind of library, it's not going to yield a lot of benefit. So it's like a hand-in-hand process. Any pair, there are separate paths. There's the network card, how long the network card takes to process a packet. There's how long your process takes to process the packet. And we have to optimize all of those specific paths. So when we're talking about kernel bypass, we're talking about optimizing the path between the network card and our process so that they can communicate directly. Yeah. So this is exactly the same thing that we're talking about, direct network card access from the user space. And like all of you can also ask questions if you have any kind of doubts and queries, and I'll answer them right away. I think that is also a good way to learn something informative because you must have a lot of questions that you have right now. So anytime you want to interrupt me, you can just speak up, and I think that'll be fine. Any questions?
Just one question.
Yeah.
So, so this technique is useful when you are loading the market data that's coming in from the exchanges,
Yeah.
right?
It's
From
no, no.
you
It's like Suhas, you've asked a very nice question. Now when we're talking about trading, for example, I think this class is specifically for low latency C++ trading and low latency C++, and that is the only two areas where it is significant is in game development, where it is very important that our frame generation and any kind of data we pull happens very fast, and that is also true in trading, where every CPU processing time counts. So when we're talking about, for example, your question was this helps in market data receiving. So right now what happens is when my network card receives a market data packet, it stores that market data packet in the memory of the network card itself. So network card has its own RAM, sort of a random access memory, temporary memory. So what DPDK and any kind of kernel bypass solution does is the network card has buffers. So there's a receive buffer and there's a transfer buffer. What the receive buffer does is anytime the network card receives the packet, it pushes it into the receive buffer. What we're trying to do is we're trying, like our application, for example, my application that wants to get the market data as fast as possible. What we'll do is will our application will constantly poll this RX buffer. It's a queue. It's basically a queue implementation, shared memory queue implementation. So what we'll do is we'll constantly ask this RS queue, is there a new map? Is there a new packet? Is there a new packet? And that will happen the CPU is not waiting on anything. All it is doing is constantly asking if there is a packet, if there is a packet. And as soon as we receive a packet, our application will get that packet, it will process it, and it will again start polling for new data.
Okay.
And the other thing is, it is also very beneficial when you're trying to send messages. For example, this is something that has a lot of developments going on right now. For example, if I talk about Cisco network cards, what happens there is you can preload the buffers. Like if I have to send an order, if I know what kind of order I'll be firing. For example, my strategy is working on a single instrument, and I know what kind of order I'm going to send when my strategy gives me a signal to buy or sell. So I will preload the transfer buffer that is on the network card. I will load my packet, my order packet, the message that is going to the exchange that I have to place this order. I will put it in the TX buffer beforehand. And whenever my strategy generates a signal, all I have to do is send a signal to the network card that send this message. So instead of me sending like 128 bytes or 200 to 256 bytes of message at when I have to place the order, all I have to send is a single Boolean flag. He empty the buffer, empty the TX buffer, whatever is in the TX buffer, send those messages. So the network card is also doing the same thing. It constantly monitors the TX buffer. The like for example, the core of the network card also has a CPU core. It constantly polls the transfer buffer so that anytime it has to send a message, it will constantly poll in the TX buffer. Is there a packet that I have to send? Is there a packet I have to? It constantly polls it. At the same time, our application constantly polls the receive buffer. Is there a packet I have to receive?
Okay.
Okay.
So the companies that ExaLab and DPDK, they provide the libraries for us to use in our C++ code, or do we write it ourselves like this, all
No,
this
no, no, no.
polling?
They provide libraries. They do not provide the TCP IP stack, TCP UDP stack. So that you have to do yourself. What all they provide is the packet you have to send and the address you have to send it. Managing the connection, actually acknowledging that the packet has been sent. If the packet, for example, that is what happens in the TCP IP stack. For example, when we're using Python or in C++, boost.beast for
Mhm.
WebSockets and Boost libraries, they manage it on your own. Like when I send a message, for example, I use uh, post or get request, the
Mhm.
library itself asynchronously, it has its own CPU code that is constantly running, like a loop that is constantly running. It sends the package, checks with the Linux kernel and everything if the message is sent, and if the message is not sent, it gives us an error, or if there's an issue with the some packets were dropped, it resends them, and it returns to us after the acknowledgement is made when we're using these libraries. So when we're using DPDK, or when we're using ExaLab or ExaSock, any kind of library networking that is defined by the network card. All of these are C++ libraries that we can integrate. But when we're using these libraries, we have to manage all of those things on our own. If the packet is sent, if the message fails. So whenever you're sending a message on TCP, if the message is received, you will get an acknowledgement message. So we have to constantly poll for those messages and other messages also.
Okay.
So
Thank you.
all of the TCP IP management that we're very used to when we're using any kind of networking libraries is something that we have to handle on our own when we're working with directly with the network card. The network card's objective is whenever it receives a packet on its port, it will forward you the packet. And whenever the packet you have to send, you'll put it in its buffer and it will send the packet.
Okay. Thanks.
Abhinandan,
Yes.
when I look at the your throughput graph, I'm a
Yeah.
bit puzzled because I don't have any Linux bypassing background. But what
Okay.
I heard was if you compare the throughput
Yes.
with the normal Linux TCP stack,
Yes.
it is
Yes.
bare minimum 10 times faster. But when I look at your graph, it's showing like at the max 3 times
I
faster
don't
or
think
3 point.
like it also depends a lot on the hardware you're using. So the benchmarks are they must have a powerful hardware when you're using, for example, when you have a four-core CPU and you all of those four cores are the kernel is also using them and your application is also using them. The cache size is low. So hardware actually plays a lot bigger role than we think, specifically in low latency. Because, for example, in trading specifically, it is very common. If I have a 8-core CPU and I have a cache of like 28 MB cache, which is like I think usual for right now current CPUs. What I'll do is I'll disable all of the cores except one or two that my application is using, so that the cache is completely available to my application. So, when you compare latencies, if you look at the specifications of any kind of CPU, you'll find two specifications. One is how fast the access of your core is from L1, L2, or L3 cache, and how fast is it from the RAM. From when you're pulling from your random access memory. That is hard, but L1, L2, 3 caches are very limited. They are very fast, but they're very limited. And when we are comparing those, the latency differences between them goes up to 10x or something like that. So when we're talking about kernel bypassing and like you said, 10x difference of 10x, it is very much hardware dependent. If you have good hardware and like, for example, I use this example specifically because there's also another chart that shows an optimized kernel. So what this has done is this has fixed a lot of the things that are dynamic in the kernel to be static for applications, to serve our application. So but when we're talking about here kernel optimized and the difference between DPDK, the only latency we experience is the process communication cost when our application sends data to the kernel and the kernel sends the data forward. Now, I can talk a lot more about kernel optimization. Kernel optimization also involves pinning the kernel to, like kernel does not do constant polling. What we want, like, for example, if I have a loop, like I talked about, looking for market data, constantly looking at the TX buffer, sorry, constantly looking at the RX buffer for data. The kernel does not do that. Kernel has a lot of other operations, so it postpones that data and it handles it through interrupts. If we optimize all of that, the only difference that will be left between the kernel and using DPDK is specifically the time that it takes for the IPC communication between two different cores, two different applications. So if you pin the kernel to a specific CPU and you pin your application to a specific CPU, then your latency will be just the communication time between those two applications. Obviously, it varies a lot, but I don't think 10x is a nice or like accurate portrayal of the difference you'll feel between using an optimized or an optimized kernel and when you use DPDK.
Okay, got it, Abhinav. Thank you.
Okay. So the core concepts for DPDK is pole mode drivers. For example, the drivers, we communicate directly with the drivers of the network card, and we avoid kernel scheduling, any kind of things. And we use memory pages and like we allocate big buffers in the cache so that if you have to like for suddenly you have to send 10 orders, and those 10 orders you can send right away. But if the buffer size is short, or if the memory that our application has allocated in the cache, the CPU cache, the CPU cache access is very fast. It's in terms of 70 nanoseconds or something. And when we talk about accessing RAM, it goes up to 300, 400 nanoseconds. And memory pools, I think, is exactly the kind of the similar thing, where we reserve memory in the networking cards memory and the networking cards cache and our CPU cache specifically. So like the packet path in DPTK is network card puts it in the receiving application. Our application constantly posts the receiving, and our application post the packets into send into the transferring, and the network card quickly picks it up. So there is no waiting time. The network card is constantly looking for packets from the port to send to the receiver buffer and constantly looking at the transfer buffer to send packets. So we've skipped any kind of scheduling, any kind of processing. What we're just trying to do is set up a clean highway to receive our messages and to send the messages. Now, what we'll do is we'll actually dive into some code, some of the code for kernel bypassing, specifically DPDK and how you can implement it. Uh, so, okay, this is, I think, initialization. I don't think this is the right code base. These slides I had as well. Okay, so what we have to do is when we're using DP, we initialize the environment and we prepare the pools. We configure the port and the queue, the specific port the data is to be received at. Uh, we use messages. For example, currently the examples I'm using, it uses mTCP. mTCP is a stack that is compatible, a TCP stack that is compatible with DPDK, so that we do not have to handle the TCP IP stack on our own currently. And what we're doing also is we'll receive UDP packets directly from the DPDK. Whenever we're talking about market data, specifically TBD data or any kind of data you will find at co-location, it is also always you'll receive it using UDP, because UDP is multicast. Basically, UDP packets are thrown by the exchange. The exchange generally has two streams or three streams, so that if you miss a single packet, you can receive it from the other stream. But UDP is a bit unreliable than TCP because there is no acknowledgement and there's no way to know for the server and the client if a packet has been missed. But it has very high throughput. So that is why you'll also always use UDP when you're receiving a buffer or market data or anything like that. Okay, so this is our main function. This is I've made a simple example for how we can receive and send messages. So here what we're doing is we set port ID. These are some of the simple things, but basically what we're doing is initializing the DPDK library so that our network card our application has can establish a communication with the DPDK. And we're setting up memory pools. Memory pools basically like the cache sizes we have to use for a single packet, the size that we have to define. And the next statement is basically if the pool is not being able to define, this RTE PKT mbuff pool create is a DPDK function. And what it does is it does all the underlying communication with the network card. But if it fails, it will return your null value. The next part is initializing the port and deciding on which port the network card will send the data. And the next two functions that we're going to talk about later is the send TCP message function, which will highlight how you can send messages on TCP from the network card. Currently, what we're doing is we're sending it locally. And the UDP packet, receive UDP packet is basically an example of how we can receive packets from the network card using the receive buffer. Okay. So this is basically the definition part. And when we talk about number of memory buffers, let's talk about from the first, define num memory buffers 8191. So what that defines is in our CPU cache, the CPU cache that we talked about, L3 cache basically, L1 and L2 caches are very small. But L3 cache, what this will do is DPDK will reserve a set of memory specifically that our CPU can access very fast and that we can use to send packets. So number of memory buffers is basically 8191 here. That is the number of packets that our memory buffer can hold. The memory buffer cache size is basically the size of a single packet. And burst size is basically how many packets when our application, for example, the receiving part, what we're going to do is we're not going to do the busy polling ourselves. The busy polling is handled by the DPDK library. So burst size is basically if I have 32 packets or 34, 36, 37 packets that are pending to be processed by our application. So we will receive those 32 packets at once. The next part is this structure, static const structure, RTE, ETH const. This structure is defined in the DPDK library. It is basically configuration for the ports. And for example, this is just configuration and what kind of how do you want to define your application? It is just configuration for the DPDK for this specific application. The next thing is we define a memory pool that is also defined. This RT memory pool is also structure defined by DPDK, and we're currently not initializing it. We just create a pointer so that later it can be initialized. For example, in the functions that we give, this is if you can see, the struct RT memory pool is a global variable. It is not defined in the main function. and it is not defined in the subsequent functions that we define. So this is a long living object that we will have throughout the lifetime of our application. Now let's talk about the DPDK init function that were defined here. So the function, let's talk about int space ret, and what return is, and what this function RTEL init does. What this does is basically like what I talked about first. It initializes the DPDK environment, and it reserves memory in the CPU. It initializes the CPU cores, sets up the memory pools in the cache, and sets up the communication between the network card and our application. And it has to be called before any kind of functions are called through the DPDK. Or where here we're passing argc and argv just because when we initialize our application, for example, when you go back to the main function, see, main function has command line arguments argc and argv. So what we're doing is passing on those arguments to the DPDK init function. Can you see my mouse? Is that visible?
Yeah, I can see it.
Yeah. So when we're here talking about DPDK init, this function defined by us, we pass those arguments so that any of the arguments that DPDK receives, we don't have to define them in code. We can directly forward them to this RTEL initialization function, which initializes our DPDK environment and links it to our application. And here it's the same. If the return value is 0, that means there was some failure with the initialization, and we return the application. Now, the step 2 part is we have to configure the port, Ethernet port details, because we're not dealing with the TCP/IP stack on all. This we have to configure and set up the RX and TX buffer, those sizes and their arguments. So let us talk about the first function. Here we're talking about, I think, port configuration default is also a structure. And RX rings, TX rings equals 1 is basically how many buffers we need to define. So inside the memory of the network card, we can define a lot of buffers. Like for example, if my application is communicating to two different two different ports, or listening on two different ports, or two different network, or basically two different addresses. So I can have different ports for those. Currently here we're using only a single. So RX rings is also equal to 1, and TX rings is also equals to 1. Now the next function is configuring the port, this function, RTE dev configure. So this function basically, it is how we want to configure a network card. So like we just talked about, defining the queues, RX, TX buffers. So port ID is basically ID of the Ethernet port. The Ethernet port can have like when you've seen network cards, there are multiple Ethernet ports or QSFP ports. So what it does is if my Ethernet is connected to the network card on port 0, and the packets are being sent there, if I put here port 1, then I will not receive any packet, I will not receive any information. So the port here is basically defining the hardware port that we're trying to listen to and define. RX ring is basically how many rings we want. TX ring is also how many rings we want. And port configuration here is just we're using default values. Here you can also look up port configuration default and what it defines. It is basically some more settings that you can tell to the NAC how you want that to process, how you want to prioritize that. So configure part is basically configuring our application is communicating to this port, and we want one receive ring, one transfer ring. And this is our port configuration where we use the standard defined by DPDK, port config default. This is a struct defined by DPDK that you can use directly. Now, what we're doing is allocate and set up one RX queue. This is exactly like setting up, we're giving the same port number here, but it is what is the size of the queue, what we want here. So here, when we're talking about this number, where we're currently giving the port and like which RX queue on that port we want to use. 0 is also ID of the port. So where the RX ring we set up first. Now 0 just means the first receive ring that we're configuring. And socket ID, I think this is also a function. I think it's socket ID. Basically, the function here is you can look up the arguments and what they do, but it is like setting up the queue. This is defining the configuration of how we want it to be, and this is defining how we want our RX queue to be. And 128 is, I think, it is the size of the packets that we want to be able to receive, the buffer size basically. 128 is the buffer size on the memory of the network card, and RTHK dev socket ID. I think socket ID is also this function basically uses the port to create the socket ID. You can call it anytime to get the current application's context. So, the ID that the network card uses. The port is something that is defined in our application space, that is defined by DPDK if you want to use on port 1 or port 2, but the network card has a different ID. And there's also, I think, a slight cutoff here in buffer size. Just let me open up this. Buffer size. Okay, pool size. Okay,
It's
so
okay.
this is,
Like you
yeah.
can name that. What is that? It is okay if it is cut like.
No, no, okay. It is basically the pool size that is configured in for example, when you're talking about any kind of memory, when I talked about the cache allocation. So we're trying to do here is DPDK has defined to basically allocate or reserve some cache on our CPU specifically for this purpose of receiving the packets and all. And it also defines reserving memory inside our RAM, because from the point of view of the CPU does not know the difference between its L1, L2, L3 cache and the memory. That is handled by the ring buffer and the IO controller. There's also an IO controller on board the CPU that handles key if it does not find a packet in the if it looking for a memory address and it does not find it in the L1 cache, it will look in the L2 cache. If it does not find there, it will look in the L3 cache. And after that, it finally picks it up from the memory. So memory mbuff pool size is basically the pool size that we want to allocate in the RAM. If we create a very big pool size, obviously it will not fit inside our cache. If we create a pool size of 100 megabytes, our cache will never hold all of that data. Something I'd also like to talk about when we're talking about here, basically memory buffer size and all of that, is that whenever we access a variable defined in our application or access any kind of structure that we have defined or any kind of object, the object gets pulled. But whenever the IO controller does not get what kind of variable it has to pull, a struct it has to pull, it gets a memory address. So what happens is when it gets the memory address, there is a cache line size. You must have heard of the term cache line size. Cache line size is basically whenever you're accessing an object, it will generally be in the size of 12 bytes or 16 bytes or any kind of size arbitrarily. You can, if you're talking about integer, unsigned integers or characters. So what this IO controller does is it pulls in 64 bytes of data at any point of time. If I just want to receive an 8-bit integer, then it will pull in data of 64 bytes from the RAM. When we are working with the low latency applications, what we want to do is when we're pulling those 64 bytes, we want to be able to pull data so that all of those 64 bytes are useful to us, because pulling data from memory is very costly. So if we fill our cache with 64 bytes of data, out of which we only want to use 8 bytes, then that is a lot of cache wasted. So I think I've digressed a bit. I think the same is here. We can set up a transfer queue. This is the configuration of a transfer queue. And transfer queue, we do not have this parameter of buffer size. Specifically because the transfer queue is set up inside the network card. So we do not need to reserve any kind of memory on the RAM for it. And the next function we have of start the port RTA dev start function. What this is, it starts the Ethernet device. So it is basically telling key we have made our configuration. We have called all the functions that we need to call. We've set up the transfer and the receive queues. We've configured the port we want to receive, how many buffers we want. And now our network card can actually start listening. The next function that we have last here, RTE underscore ETH, this promiscuous enable. This is basically a function that we use for testing. So when we give it this port, what we're telling it on this specific port, any packets we receive on both of any kind of if you have two Ethernet ports, any packet we receive is transferred to this specific application. So, for example, we started with port number 0. I think, yeah, port is defined as 0, right? Yeah, for example, if we're using port 0 or port 1 traffic is also directed to port 0. So that this is just for basically for testing purposes, so that we know all of the packets received on our Ethernet card are directed to our application regardless of the port it starts with. Now, let us talk about sending a message using the mTCP stack. And here we define in integer sock ID and sock adder. Just let me open my notes. Please give me a minute. Okay. Okay. So, for example, the sock FD integer we defined as such. The structure defined niche, sock addr underscore in, is also a structure defined in DPDK library. And currently we're not initializing it, we're just declaring it that a function will use it. And like the next function mTCP in it is basically initializing the TCP library. We're currently assuming we're using mTCP. So mTCP configuration is the configuration file. It also has a lot of parameters on how you want to configure your TCP stack. And that is not what we're going to get into today, because TCP configuring your TCP, there's a lot of things like how soon you want to poll. So there's a lot of things you can do to configure your application when you're using any kind of library. So this function mTCP in it is basically like initializing that TCP stack, and it reads from the configuration where it basically reads the settings. And what we're using is we're using mTCP. So for communication, we're not using our own TCP stack. Now the next function is mtpc create context. Now this is also important. mtpc and DPDK, it has to know the core it is currently working on. That is communicated with the network card. So that is also very important. Our application has to be CPU pinned. That our application should only be running on a single CPU core. It cannot happen if our application is running on core 0 right now and the kernel switches it over to core 2. So this is basically defining the network card or the CPU core that our application is running on. So the network card can directly send packets to that core. The other function is mtpc create context. And what this function does is it basically creates a TCP context. Context is basically a set of information that is going to be used by a further function that we can pass around to basically pass around information. So it is a context of our application. Basically, each core usually runs its own TCP stack, for performance reasons. So that, for example, if we get to the same problem, if we have a TCP stack deployed on multiple CPU cores, or a single CPU core and multiple CPU cores are using those CPU stack, we again get to the problem of inter-process communication. And we get to the same point where we have to like communicate with the kernel also process, and all of that. The next function we have is sock fd, that the integer we defined above, and that is what we get from the function mtcp socket. This is also function defined in the mtpc library. What it does is creates a TCP socket inside our stack, and it works very similar to socket in Linux, which is creating a virtual socket for our communication. And the socket here currently, it is in Linux generally you can access sockets between multiple cores, multiple applications. But here we're defining the socket specifically for our application. That is why we're also defining the core, the CPU core that is using to communicate. If we're talking about the arguments, the first argument that we're providing, mctcx, is exactly what we defined before, which we use the mtcp create context function, which creates the context, and that is passed along to this function, socket creation function. And the domain is basically AF INET is also constant defined. AFINET is specifically for IPv4 communication. For example, you also find this constants for IPv6 and any other kind of protocols. type is basically socket time. If it is for TCP, we use socket stream, and for UDP, we use socket datagram. This basically defines the type, like for example, like I talked about the TCP IP stack and how that basically handles all of the underlying communication for you. So this is exactly that. We're just telling it that this is a stream socket where our communication would be done using the TCP stack. The last is basically protocol is I think it is a system default setting. Okay, protocol is I think uh, the underlying IP and Ethernet stack, Ethernet functions. When you were talking about I should have a diagram, currently don't. But when we're talking about a message that is being sent on a network, your message, consider your message in a box, and all it has all the details. If it is using post method, get method, the actual content is there. Outside of that, when you're using a library like mTCP or any kind of library, there's also a TCP IP stack on top of it, which contains the addresses. And then there's another data on top of it, we can think of it like a JSON. So the innermost JSON is our message. On top of that, we have the kind of message we're sending, the format, content type application JSON, or content type XFORM, double XFORM URL, all of those things. On top of that, it is nested inside another JSON, which defines the address and the protocol we're using, UDP, TCP, IP. And on top of that, there's the Ethernet frame. The Ethernet frame basically defines how the message is sent. That's also something I think that would digress from what we're currently talking about. Okay, so the next function we're calling, I think is address family. This is also in constant. The next method we're calling that is important is this method mTCP connect. Now this method is basically, the TCP socket that is connecting to our application. So for example, the network card is connected to a network and it can receive messages from a lot of applications. So when we're connecting to a specific ID, like here we're giving it server IP, right? So this is something we defined in the main function. Yeah, so send TCP message, we have defined these two protocols and these two arguments, sorry. And we're using the first argument is the server IP, the second argument is server port. And this is what we're giving basically to the connect function. What connect function does is it communicates to the server. We want to start receiving or we want to send messages, and the acknowledgement and any like if you've received the message should be sent to this specific socket. So when our network card receives the message, it will know the socket is assigned to this application, and here we have to give the response for it. Also, there's the callback function we defined here. After that, if mTBC connect is not, it will give return a connection failure error. And the next part is we define a character, the string message, hello from DPDK TCP. And what mTCP write function does is just send data through the established TCP connection. So what we've done here is, for example, this might be a bit different because, for example, first of all, we talked about RX buffers and TX buffers, and that's something that you have to deal with when you're working directly with the network card. So what we've done here is we've used a custom TCP stack. So this is an example of how you can go ahead and directly use DPDK with integration with this mTCP library. I think it is, yeah, it is compatible with DPDK. So what we're doing here is we're abstracted away all of the things that I talked about, the RxTX buffer, but it still communicates and does things the same way. So we still had to define the buffer size, we still have to define the TX size and all of that. But for example, in this function, send TCP message, this has not a lot of relevance to specifically kernel bypassing. That is being done in the background. A lot of the times when you're working with low latency network cards, this is not how you're going to do things. You will have to build a TCP IP stack of your own. But this is a simplified example of how you can use mTCP connect. When you're working with directly with the network card, you can build something that will give you a lot less latency than mTCP. but this will still be much faster than using direct Linux network calls, because this is in theory this is underlying, this is communicating directly with the buffers, directly with the
So
networking buffers.
one quick question.
Yes.
So so this message string, right? The const-char message. So that is
Yes.
actually that will actually be the order that we want to send to the exchange, correct? It could be
Yes.
a
Yes. Yes.
fixed
Yes.
message, it could be some other format, but that's the actual message we want to send,
Yes,
correct?
yes, that's the actual message you send to the exchange. Here it is
Right.
a simple string message, but this is not actually what gets sent. What mTCP is doing here for us, it is taking that message, attaching all the headers that are needed for the TCP/IP stack, then creating the Ethernet frame, and then pushing it to the RX buffer. Oh, sorry, TX buffer, and the network card picks it from the TX buffer. And
Okay, so
I'd really like,
because we
yes, yes, yes.
sorry
Please go ahead.
because we use this high level abstraction of the
Yes,
mTCP library, we didn't have to go down to the level of the buffers, correct?
yes,
So
yes.
okay, I
So
see.
when you're dealing with buffers, that is, I think, if I would have showcased your case for the code for specifically the buffers, that would have been a much simpler thing, because all we have to do is we have to push data to the buffer, and the buffer then Ethernet our network card sends that message to the exchange. But what we lose there is all of our processing, the acknowledgement that we receive, and if you have to resend a message, if the packet has been lost, all of that has to be done in our application itself. This is still
Right.
being done in the application, but this is being done using the mTCP has already done that. So currently what we're doing here is using that. So here we have like a lot of constructs on defining the streams and like what kind of protocol we use. For example, if we talked about AF underscore INET, that is basically telling mTCP socket that we have to use IPv4 communication. If we're
Right.
talking directly about buffers, all of the processing that is happening, the packet framing and the acknowledgement, the protocol, we have to implement that on our own.
So what
That
is more
can
common? What is more common in the industry? Do you actually like,
more common in the industry is not using mTCP like interfaces. It is directly like the companies like Tower Research and Quantex, all of those companies and the big HFT firms, all of them have developed their own solution, their own TCP/IP stack. You can do one thing is much simpler. For example, TCP communication stack is harder to implement because there's a lot of steps. UDP is something that, like for example, if you want to if you want to understand buffers and how they work, UDP is much simpler to implement. UDP is something that you can do on your own. And for example, now that we're talking about it, currently the latest thing that's happening in the firms is they've moved on from this TCP/IP stack in the software application. What they're using is they're using an FPGA. I guess if you're familiar with FPGA, are you guys?
I have just heard of it, not really familiar.
Okay. FPGA is it's a whole different topic. Well, it's
Right. It's
we
much
can we can
harder, right?
we'll go
Yeah.
there. We'll go there in the further classes. I'll have a specific class just for describing FPGA and how that can be used. But what we're doing here is basically the TCP/IP stack has been implemented for us. We cannot change its latency. How it's written, and we have to deal with that. If you want to go with something specific, you want to go to lower latency, you can build a specific solution for yourself. That, like for example, where I talked about when you deal with this is not this library particularly TCP/IP stack is not compatible with ExaSock, which I talked about before, where you can create and put a packet in the buffer and you can fire it later. So I don't think any kind of public open source library works with this ExaSock or those kind of solutions that are super low latency. So when you're working with those, DPDK is still something that has a lot of support, and that is available through a lot of, you can use it on Intel network cards, you can use it on Xilinx network cards, and you can also use it Cisco network cards. But it is like a general solution. So you'll always get higher latency when you're using something uh, that is card agnostic. But when you're dealing with a library written by the vendor, for example, a library written by Xilinx and Cisco, Cisco particularly has the lowest latency solutions right now. So those are much higher, much better optimized,
Is
specifically
is
for all of this.
is Solar Flare still in the market?
Yes, yes, Solar Flare has been acquired by AMD.
Okay, okay
Yeah,
then.
the Solar Flare and Xilinx network cards, both of those come under the guise of AMD.
Okay, thank you.
Okay. Any other questions? Anybody else? Like I'm very curious to know if you have any kind of questions on anything else that you might not be able to understand or you're curious about.
So how's the performance varies to the libraries such as DPDK or
Yes.
Solar Flares Open on Road or
Yeah, yeah.
TCP Direct, which is the lower uh, version of Solar
Yes.
Flare API. And I know there's also libVMA. Yeah.
Yes.
So what's the fastest or
When we Minisoc, you got
yeah,
a nice question. But when we're talking about all of these, the most major difference that you'll see is when you remove the kernel. So all of these solutions will not have a lot of drastic latency differences between them. Some of them will have some differences. For example, you can shave off 200 nanoseconds, 150 nanoseconds. But more or less, when you've removed the kernel and you're communicating directly with your application, directly with the network card, your application is communicating directly with the network card. The latency is more or less the biggest chunk that is generating the latency is already gone. The kernel is the biggest hurdle because the kernel is not designed to work with a single application. It's designed to work with a lot of applications. So it is designed to handle requests and delay those requests, schedule those requests. So you're not gonna see a very big difference, but obviously the big HFT firms, they're always looking to, for example, 200 nanoseconds, 300 nanoseconds, something that can make a lot of difference in the market. Because when you're working on a strategy, when your system is working on a strategy, and that strategy is something that is very common. For example, if you're doing arbitrage, statistical arbitrage, and basically plain arbitrage between future to future. For example, if you're trading between the spread of two futures, this month, current future, next month, you can see that their prices are very tight. So when a spike happens, when those prices change, you have to be as fast as possible. And somebody else is also running on that same strategy. They're also trying to bet on that spread. So those 200 nanoseconds or 300 nanoseconds can make a lot of difference. But the major chunk of the difference you'll see is you'll see microseconds shaved off just by removing this kernel bypass. Sorry, removing the kernel from your network stack.
oh yeah, I got it. So it's just like there are differences and some
Yeah.
API or specs differences, but there are not a microsecond impact, you know.
Yeah, yeah. When you remove the kernel, that gives you the most benefit. But also
Oh,
when you're going for the lowest latency solutions, I think the currently available solution that's the best is Cisco network card. And if you want to go below that latency, for example, I think everybody here is interested in specifically for this for trading purposes. So the lowest latency is you see is Cisco has a network card that is an FPGA on board. It has a FPGA is basically hardware that is programmable. So you can create logic gates and you can create logic gates and use registers to store data. So when you do that, the lowest latency, I think the current record is 9 nanoseconds, where the message was received on the network card and the order was sent from the network card. That is because the network card itself has that FPGA on board, and the FPGA has logic gates instead of a single processor processing one instruction at a time. It's defined like a logic gate based hardware that runs in a single phase. You want to send different orders for four different instruments, you can do that in a single run. So when we're talking about FPGA, when you're talking about CPUs, we have frequencies in the order of 3 gigahertz, 4 gigahertz. So it can process a lot of instruction, but it does that sequentially. FPGA has clock cycles in the phase of 500, 600 megahertz. But what you doing there is you do not have a CPU that is pulling an instruction from memory, taking the arguments from its own cache or memory, and doing a computation and then moving on to the next instruction. FPGA has everything like predefined. Basically, the hardware, it is coded inside the hardware. So there is no CPU. There's no CPU that is pulling instructions from memory. Everything is in the hardware. So that is where you will see the most benefit. For currently the market is not like you'll not get a lot of benefit from working with kernel bypassing when you're talking about ultra low latency, because everybody else is currently moving away from this, moving the TCP stack onto the FPGA. For example, you don't have to like do all this message creation, creating the Ethernet frames, creating the TCP IP frames. You don't have to do that in your C++ application. Your C++ application will send the message to the FPGA, and the FPGA will like it is hardware coded logic, so it is very fast. So that TCP IP message framing is done there, and that will also give you a lot of benefit. Basically, any kind of processing that is done on the CPU, the most, if you can offload that, then you'll get a much faster system. So it's not something like it's not a very simple problem, latency. When we receive a packet on a network card, there's the processing time of the network card. There's a processing time it will take to send it to its memory, and how fast that memory
Hello.
is.
So, hello.
Hello.
Yeah. So, Nandan, what I'm saying that the timing is up to 8:15. So already
Yes.
8 o'clock. So if any
Okay.
other slides you want to like to show or explain, so you can explain 8:15.
Okay.
Like
Okay. I
8.
think yeah, sure. I think I have a couple more slides. This is receiving. This is basically the code for receiving the UDP packets, and you'll see something similar here. What we're doing here is, what we're doing here is we're creating a buffer, and for buffer size plus plus is basically we're using batch processing. So for example, here we have integer I equal to 0, I equal to NBRX. NBRX is basically we're defining how many messages do we want to process in a burst. So what this does is it reaches out to the network card and it takes all the packets that are available. If they are less than our buffer size, if they're less than the burst size that we talked about the constant here, we can see the first statement is setting the burst size. If it is less than the burst size, then our this for loop finishes. If it is more than the burst size, then it completely takes just keeps on taking the packet. And the code is, I think, pretty straightforward. Extract the UDP. All of these are proprietary functions. These proprietary functions for our library mTCP. This basically does is like, for example, here ignore non-IPv4 packets. This here is specifically because, like I talked about before, we were using that function key, any kind of data that is received on an Ethernet frame gets forwarded to that application. And we do not want to receive any other packets than IPv4. And this is basically the same thing. If you guys want, I will provide you all of these slides. And now I just wanted to talk a bit about ExaSock. It is basically ExaSock
Can I
is
ask
some
just a,
yes.
can I ask just a very quick question?
Yes, yes, yes.
So we are basically reading packets, right? So w- the data that's coming in, let's say from the exchange, right? The maybe the prices and the
Yes,
volume,
yes,
all that
yes.
data, it may not fit in one packet, right? So it could
Yes,
be like
yes. You're very
made
much
up
right.
of multiple packets.
Yes.
So how do we handle that in our C++ code?
No,
We kind
currently,
of
like
read.
the examples that I've shown you, we're using
Mhm.
the mTCP library, right? So if the message is split into multiple packets, the library handles all of those. But when you're dealing with an application that you're using directly working with the sockets, sorry, working with the direct buffers of the network card, you will have to handle that yourself. What the exchange does is when you receive a packet, you unload the TC Ethernet frame, and then you unload the TCP IP frame, and then you get to the actual message. The actual message is generally in binary because binary is very fast. But if you see the definition that a lot of exchanges have, they have for a single message, they have characters that tell you that the message has ended. So if you receive a packet and you see that the message has not ended, then your application has to handle to keep on receiving more packets and appending them to your already received packets to
Okay,
basically
okay,
until you have that ending character, until you have that confirmation from the exchange that the current message has ended.
okay. So one packet might have that character and then the beginning of the next message.
Yeah.
So
Yeah, if
right.
it might like that is something that is handled by network. But the simple part is the exchange tells you that now a message is ended. And if you keep receive a packet and it does not have that end, you take the next packet and it might have that end in the middle or any kind of data. So yeah, exactly that.
Okay. Okay.
Multiple,
Thank you.
that is how you handle multiple packets when you're dealing with the application on load. ExaSock is also something developed by this Cisco, and there's I think also a similar solution by SolarFlare. Open load, I think open load is the name. That is also kernel bypassing library. These are very simple libraries that if you want to develop a low latency application, and it's like your strategy is not very much dependent on exactly being ultra fast, but it is dependent on being like it has to be in the order of microseconds, but it doesn't matter. Like if we're talking about super low latency, those 200, 300 nanoseconds do not matter. This is something that is much simpler to use. So when we talk about ExaSock and open load API from SolarFlare, what these libraries do is when you're designing your application, you will use this is also like you do not have a TCP/IP stack. You have to use all of them. I think you can use them with some libraries, but what they do is you compile your application with their library, and it automatically converts all of those. It redirects all of your networking calls directly to the network card. So if you have a normal application that uses Linux sockets and your network calls are going through the kernel, you do not have to change your code. You don't do not have to do anything else. You just have to compile your application with along with this library. You have to attach it, and it automatically converts your application into a kernel bypass application. So you'll get most of the benefits of kernel bypassing from just attaching that library, and it will convert all of your networking calls directly to through a kernel bypass one, or communicating directly to the network card during compile time. So when you're compiling the application, the compiler knows this library is linked, and this library automatically converts your networking calls. It does not convert your calls, but it creates a wrapper around your application where any kind of Linux calls are caught by this, and they are directly forwarded to the network card. And this is a ExaSocket basically code, a simple example. I think this is not right. I think this is not ExaSock. And helper abstractions. Exalib is what I talked about here at the beginning, where we do not have a TCP/IP stack. But what we can do is, like I talked about, we can send messages directly to the buffer. We can pre-register packets. We can pre-register message to the buffer, and as soon as I receive a market event, I don't have to send all of that message to the network card. The message is already there. All I have to send is a trigger to empty the buffer, and the message is sent very fast. And I can define the size of the buffer. There's a lot of things. Yeah, I can define if I want my traffic to be forwarded to two different sockets. A single application listens to a single socket, a single thread listens to a single socket. So if my application has 4 threads and all of them want to listen on 4 different streams, like 4 different instruments, then I can configure this library to basically do the forwarding itself. So if it's not that my application receives messages 4 instruments and I forward those 4 into my other threads, that is processing that strategy on that instruments, that is handled automatically and directly. Exalib is specifically for network cards of Cisco that have an FPGA on board. So all you have to do is use this, and it will automatically use the FPGA to direct your packets instantaneously. When you are using our application, we have to go through a loop. We have to go through all of those 4 packets and put them into different queues that our strategy thread can pick up from. So what this does is basically instantaneously pushes those packets. So this is also a part that can help you reduce latency a lot in your application. That's anything that you don't have to handle inside your code. That is something that will help you reduce your latency. Anything
So
you can
this,
shave off from the CPU.
so this is really good, right? Then we don't have to deal with the
Yeah, there's a
with
lot
the
more
limitations,
options.
right?
There's routing, there's a
Right.
lot of things. So this is something that is this is a very new library, not in the sense of 1 or 2 years. But these are all solutions that the companies have made specific to their hardware that you can use to reduce processing on your end, and they've optimized it for their hardware. CPU is a very generic thing. If you're using Intel CPU, AMD CPU, they're agnostic to what you're trying to do. They're just trying to do everything. They're just trying to make hardware that it is possible to do everything. What these libraries and these network low latency network cards vendors are doing is they're trying to figure out what you want to do and try to build hardware optimized towards that so that it is fast and your CPU does not have to deal with it.
Right.
Yeah.
Any
Abhinandan,
idea how?
Yes, yes,
Any
yes.
idea how much the Cisco NIC costs? I'm sure it's very
Actually,
expensive.
my firm has currently bought this for network card. The cost is, I think the cost was 3.5 lakhs for the K3 10 gigabit network card.
Okay.
Okay,
And
so it is very
what
costly,
about what
and
is the a
yeah,
little more like 50 or 60 gigabytes? Probably very expensive.
yeah, that goes up a lot in value. I think it's
Right,
4 or 5 lakhs, something like that. Like my
Okay.
entire my system, the 70% of the cost is for the network card.
Okay.
And when we're also talking about this, the current network card solutions that are offered by Cisco, if like I talked about the FPGA part, Cisco also offers, I think, a solution for the TCP/IP stack on the FPGA, and that goes up to, I think, you have to give 20 lakhs upfront, and it's 16 or 17 lakhs, something like that, 16, 70 lakhs yearly cost, licensing cost. So all of this hardware gets more expensive the
Right.
more enterprise level and the more low latency solution you're looking for.
And then the
But yeah,
Exalib, the library and everything just comes
no,
with
no,
the if you
that comes with the
yeah.
network card.
Okay, got it.
ExaLib and ExaSock, both of those come with the network card. But when you're trying to use FPGA-based features, for example, when I talked about the steering part, the flow steering, that we want to direct a packet to 4 different sockets, or we
Right.
want to do any kind of processing inside the FPGA that is pre-built defined, they've given a lot of options. For example, this ExaLib also have a FPGA-based function, but that will not be accessible to you unless you have that license. And the license is very expensive.
Right.
Yeah. I think I just have one
Abhinandan,
more slide. Yeah.
you mentioned that big HFT firms like the one that is based in Noida, I forgot the name you mentioned, Tower Research, right?
Yeah, tower
So
research.
they have customized TCP solution, right?
I do not have a I do not have concrete answer on that, but what I'm aware of is that any kind of firm that does arbitrage or that requires ultra low latency, they will always have their own TCP/IP stack because
Okay.
because when you're running strategies of ultra low latency, or market making specifically, all of those things, you're competing with a lot of other players, and when you're competing you just have to be the best, and they have a lot of teams. I don't know if they have a, like, you do not have to implement all of the TCP/IP stack. What you have to do in like C++ and low latency C++ is only work with what you need. So what they'll do is they'll implement the UDP and the TCP/IP stack only limited to the functions that they have to use, only limited to the messages they have to send. So
Right.
that is
My
why,
question is around that. Do they really go into minimizing the TCP stack, or they can just simply go to a better solution of kernel bypassing, right? I'm confused in that part. Meaning, is there a
I'm
point
not
spent?
really aware about the dynamics in tower research, but I have someone at Context, and what Context does is I was in contact with Context, and they were looking for someone that can rebuild the open SSL library for them that can reduce the latency. So they're constantly working on reducing the latency. Any HFT firm is constantly trying to move away from generic solutions and build something that is faster. So they were looking to build the open SSL library because NSE encryption has been as encryption has been implemented by NSE, I think since last year. Since March, it was enforced before that. And so it's been a long time that a big part of latency is also parsing,
Hello.
decoding and encoding encrypted messages.
Hello.
Yes.
Nandan, so meeting will end in 2 minutes. Like
Okay.
it will schedule. So like if any, so like if you want to wrap up and like if you can like
Okay. Okay.
summarize and all. Yeah.
I think the last talk we had have summarized. These are the only solutions. There's a lot of things you can do to reduce latency, but some of those are very complex. The easier thing that you can do is use ExaLib library, and you still have to deal with the TCP/IP stack on your own. And there's like a lot of solutions, but there's also a lot of work that you have to do to get them to work. So when you're using kernel, it offers you a lot of flexibility. But the best solution, I think, is like when we talked about DPDK, and you use a mTCP or any kind of TCP stack that is compatible. That is something that is easy to use, easy to implement, and you do not have to spend a lot of time reinventing the wheel on your own. I think that sums up exactly kernel bypassing, what it is and what happens. I think like for example, this is also a slide I had. It's very challenging. And the other thing I really want to talk about is if your strategy is something that is taking a lot of time, so calculating a lot of metrics, and your strategy goes the processing time or the calculating time, the CPU time for your strategy goes up into few microseconds, then these very low latency solutions are not really suitable for what you are trying to do.
Yeah, so if your strategy is taking longer
Yeah,
and you're doing all these expensive kernel
yeah,
bypass challenges, you will still lose out because your
yeah.
strategy has, yeah,
Yes,
so
yes, yes.
it's
No,
not adding any value.
it's not really losing out. It's about saving development time. So if your strategy is something that latency is not very critical for it, if it works on 3, 4, 5 microseconds, then just use ExaSock or any kind of kernel bypassing solution that
Mhm.
captures your application's data, and you'll be good to go. Like it will be a very small percentage difference between the latency that your application is actually experiencing. When we talk about trading, it is always measured in tick to trade time. And tick to trade time is when the packet is received on the network card. Market event is received on the network card, and in the order they actually send. And if 80% of that is part of your strategy, then optimizing that 20% to be smaller by 2 or 3% is not really going to yield you any kind of benefits.
Right, right.
Any other questions, guys? I think nobody has any more questions.
Will you be sharing the slides later?
Yeah, I can share you the slides. You can. I'll share you I think the directly code file I'll share you
So all
that I
the
use in
this
this room.
Zoom recording and the slides I will
Yeah.
share on the LinkedIn. So
Okay.
don't worry. Yeah.
Okay.
Okay, thank you.
Okay, Pranay. So we can end the meeting, right? I can stop sharing.
Uh, Hello.
Hello.
So the slides completed or like anything left?
No, it's completed. I think that was
Okay.
last slide.
So guys, this was the mock session of like kernel bypass, that is of like a kind of HFT syllabus. And the guys who is interested by seeing this mock session can let me know on my LinkedIn, and let's enroll and by paying the fees, and then we schedule like proper from first class to like all this like 3 to 4 months, all the HFT syllabus from basic to advanced level, and he will take the classes, and on which day he will take like what will like how many sessions per week, that we like all the syllabus and all these things I will let you know. So if any questions regarding the like this HFT course or anything, you can ask but the syllabus and the sessions like weekly, how many sessions, like it can be kind of like 1.5 hour sessions or like max two. So like if any questions before enrolling, you can ask here and to me or Abhinandan, so he can answer. We can wrap like this meeting in 5 minutes. So feel free to ask. Yes, Ivan, you can ask. Yeah.
Pranay, I have a question. So if you can share the syllabus that is practically
Yeah,
possible,
that syllabus,
not like
as I
just a
told
concept.
you, that syllabus that I and like Abhinandan will like finalize it, like weekly sessions as per that, like all the syllabus and all. So that I will share on this LinkedIn personal DM and all. So this Zoom recording and these slides and the syllabus and the upcoming weekly schedule. So I will share all you by tonight. So
Okay,
yeah,
thank you.
if yeah. Yeah. If any, yes, Sivan, you can ask the question. Yeah.
Sir, will foundational concepts be covered in this course? Like, I am a college student, so I might find difficulty in understanding some terms, technical
Okay,
terms.
Sivan, yeah. So the thing is that, yeah. So Abhinandan has already mentioned his concern. So the guys so I will clear here only. So the guys who is joining this course should have knowledge of C++11 knowledge at least, little like little DSA concepts and operating system. So like all this like basic things like computer network concept like TCP/IP or like any other things like OSI layer. These are the basic things. But if time Abhinandan have like it will be not like a full-fledged basic syllabus will be covered like because it is pure HFT C++. If we cover that basic syllabus, then HFT syllabus will be pending, and then this course will become a 5 months or 6 months course. So so basic knowledge should be having like whoever joining, but in between like some like computer network concept like OS concept like the cache memory. So when he takes the class so in between classes like someone don't know cache memory and all, so he can mention and he can explain. Abhinandan, if I'm right, like you can mention like what
No,
if
no,
I'm
I
saying.
completely understand this point.
Okay.
You do not really have to have a lot of DSA knowledge when you are working with low latency C++ because we're not trying to solve very complex problems. What we're just trying to do is do something very fast. So, whenever you have any kind of questions or concerns, I will give you a brief answer, and obviously we'll cover everything from within an order. So that,
So
like for
actually he's
example, the current
asking.
lecture was a mock
So
session.
so
Yeah.
yeah, you can answer. Actually, he is asking that question. So what will be the prerequisite? Who will enroll this for this course? Like
I
what
think
should
the
he?
prerequisite should be you should be familiar with C++. You must have coded in C++, and you must be aware of dynamic and static memory. See how stack memory works, and that is something I also teach you. But that should be something that you should be comfortable with learning more
You
about
are
the C++.
saying that at should someone who is joining, he should have at least be aware of like little memory management C++ concepts.
What I think is you just have to be a bit comfortable in reading C++ code.
Okay.
I'll explain to you everything on what happens, but
Okay.
the basic things like what a pointer is and what a variable data types are,
Okay.
and yeah,
Yes, sir.
all
Sure.
of the other things I think I'll explain in the course. Those are not very big concepts,
Okay.
but those are very fundamental statements, and that is something that when you keep working on something you'll understand. But I don't think it's very much required.
Okay.
You just have to have a basic understanding of how languages work and how data is stored.
So Sivan, your
Are there
query resolved? Like any
I have
questions?
another query. Like, at the end of the course, will we have a project like a full demo, a small scale HFT system? Will we be able to implement, like, to show in our resumes for placement?
Capstone project he's asking you.
Okay, that I think that is up to Pranay, not
Okay.
something that I have to decide.
Yeah, okay. So Sivan, I will let you know. So like this, like he's actually asking like after the end comes like little
Yeah,
basic not.
I
Yeah.
think after everything that I've taught you, I can give you projects that you can work on, that you can showcase in your resume or your GitHub, that basically highlight that you work with, for example, the things we'll learn, the low latency data structures, shared memory applications, and anything that is related to low latency. You can build some few solutions. For example, an application, C++ application that distributes market data to multiple applications.
So if I'm
And
if I
yeah,
if I clear this, so it will be not a capstone project of making full HFT system. It will be a part of that, like making an OMS or something like that or something kernel wise. So it will be meaning parts of that project. Correct?
yes, yes, yes.
Okay.
are there any
And sir,
hardware requirements like because obviously we don't have network interface cards, right? So is
I
there
don't.
any like
No, 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 no. You don't really need network interface cards. Network interface, NIC is specifically important when I was talking about the kernel bypass thing. But as I've
right?
already explained to you, a large part of low latency C++ application
So,
programming
so Harsh,
is like,
actually, the
yeah,
thing is that some things like network interface card or something that it is like something like you have to buy so many things and all. It is like if you know the concept, like suppose he today he like explained the concept of DPDK and other Cisco cards and all, or this library. So if you know the concept, all these slides that he made, like in upcoming sessions that we decide. So it is not like you have to write network interface card and then you have to code it in your system and then to build the system. It is like if you like understand the concept, like DPDK, how we initialize, how we send the messages, how we actually use the DPDK for optimizing the latency. Like it's not like only you run the code in your computer, then only you will learn. So like this code snippets, all the codes, it was the snippets only, but code that Abhinandan will share. So you can take as a reference and means like just for if you know the things, you can implement like in your like wherever company you want to join, or like
No,
it's like that.
I understand. I was just giving an example of
Yeah, yeah.
it.
So,
So
Suhas, I'd
what kind
also
of
like to add key all of the code that we'll be working on. You'll probably need a Linux machine, any kind of Linux machine. The CPU
okay,
does
yeah,
not
that's
really
what I
matter.
was asking. Like
Yeah, but the chunk
what
of the
should
part, the chunk of the code base that we'll be working with will be network card and independent of any kind of hardware. So you do not need to have any kind of specific hardware. For specifically when we're talking about shared memories and some low latency lock-free structures,
Yeah.
Linux
So
is
Sivan,
recommended.
So Sivan has asked one more question, that he is saying that ultra low latency strategies will become so Sivan, so this course that he is taking, he's actually taking for if I clear for all whoever's seeing this recording or like who has joined this course. So this course is only for learning the how we can make a ultra low latency or low latency level C++ HFT platform, and then strategy making that HFT level as a strategy making, that is a different thing. So these things will not be covered in this course. Am I correct, Abhinandan?
Yes, yes.
Okay. Yeah.
Pranay, I have one more question. Will you be providing us the recording sessions
Yes,
of
yes.
all the classes?
So whoever missed the class, so recording will be provided. I will make a private Google Drive link. So you can refer this Drive link. You don't have to there will be group also, Telegram group, and I will share the all those resources, slides, and all, like Abhinandan will share. And like I will make a Google Drive link where I will like upload all the Zoom sessions. Whoever missed, they can watch it later. Yeah. And I will make a Telegram group where all this, like which books to refer, or like for low latency, for example, like for C++ template meta programming or something, like anything that any book is like good that Abhinandan know. So he will like share, but that will be a private group. That will be not a public. Whoever enroll this course, that only they will get access to that, all this Google Drive or Telegram. Any more questions? So we'll wrap this meeting in 5 minutes. So if any more questions, feel free to ask. Guys, any questions? Okay, I think there's no any questions from anyone. So Abhinandan, we can wrap this meeting here.
Okay,
And
Pranay.
yeah, so I will share this like this recording to whoever attended and who didn't attend
Okay.
it. This
sorry,
this is
Pranay,
only the mock.
one quick question. What is the schedule of the classes you have twice a
So
week
the
or?
schedule, so it will be mainly in the evening only. But the evening what timing? That like I will like decide with the Samnandan, and how many classes weekly, like for what hour and what timing. All things will I mean send to the LinkedIn private DM, and the syllabus itself. All details will I will share today. Yeah,
Oh, okay,
yeah.
all right.
Yeah.
Thanks.
So, and this today's slides, this was the only mock session. And from further upcoming slides, there will be no sharing publicly to anyone. That will be whoever enrolled this course, so they will get access to that. Yeah. So now I'm wrapping this meeting. So Abhinandan, so I'm wrapping this meeting here.
Yeah, sure.
So we will connect later after
Okay,
this
okay.
meeting. Yeah.
Okay,
Yeah.
okay.
This was a very very nice session that you taken and like explain the concepts of DPDK kernel bypass and everything.
Yeah, yeah.
Yeah. So in upcoming sections, you will run the code and will show the differences and all these things. Correct, na? Linux.
Yes, yes.
Okay. Okay. Cool.
Okay.
Okay,
Okay.
guys. So like I'm closing this meeting. Like, thanks for joining this mock session.